words about the defense and about Roxana. In thinking about Roxana, there are two things that I wanted to kind of stress. There's many things I could stress, but there's two I'm going to highlight. The first is what a pleasure it's been, and I really mean this, in watching her become a scientist. That wasn't necessarily part of the plan. So she has an engineering background as an undergraduate. She came to medical school. She was very involved in medical school life, and then came to my office, Clark Center. I remember it very well. And I don't remember why, but she said, I think I might be interested in doing a little research project as part of my medical school training. So I said, okay, and as many of you might know, we have a program here, the Medical Scholars Program. I said, why don't we apply for a quarter or maybe even 3/4 of funding so you can get involved in a project. We had recently had other medical students who had enjoyed it. And so she did that, and she wrote a beautiful proposal in the area of warfarin response, which you're going to hear a little bit about today. And it did very well, it got great reviews. And then she started working, and then she said, you know, Russ, I kind of like this research stuff. Howard Hughes has a one-year fellowship, the Howard Hughes Medical Student Fellowship. Maybe I should apply for that. And of course I said, well, yeah, you've been doing great. Let's apply for that. And she applied, and she was successful with that. And then she comes into my office at some point and says, Russ, I think we should just have me do a PhD, because I think I'm really enjoying this, and I now consider it to be part of my identity. Like, I would not be whole without having and really, I mean, you might not have used those words, but that was the idea. This is an important thing that I want to do. So of course I was thrilled, and she decided to join the genetics department, which was, as you'll see, a perfect fit for her. And then she was involved in several projects, and you're going to hear really only a subset of the projects that Roxana's worked on, where important scientific discoveries were made, both methodological advances as well as new knowledge, and it was just nothing but a pleasure. And just to see from I'm in medical school and I might want to try out some research to what you're about to see is extremely satisfying. And it's extremely satisfying, of course, in the context of an MD, PhD training, which some of you may know I'm personally fond of. I'm a product of that, and so it's always fun to have somebody in the lab do that as well. Now, the second part of Roxana that comes to mind immediately is how good she is at bringing people together. And first of all, this is a pretty good crowd. The U.S. is about to play in an hour. I'm sure a lot of you will be leaving exactly at 1. But really, Roxana has been remarkable at all levels of existence at bringing people together. What do I mean by that? So, at the most basic level, she helped start up some lab efforts that we're doing to get together and have tea and have cookies. And it was a number of us, but Roxana, when she heard the idea, was the one who really said, yes, we must do this. But more importantly, she brought together the work that you're going to see on warfarin today involved, if not a cast of thousands, a cast of hundreds of people collecting samples, sharing data, and an incredibly complex scientific collaboration that normally you would never let a graduate student, no less a medical student, organize. But she did it, and she did it beautifully, and she is respected as a colleague and a collaborator already by people all over the country, who you could call up right now and who would testify to that. Florida, Chicago, all over. She also brought together, and also in work that I don't think we're going to hear about, or we're going to hear about the Iranian Genome Project. So there is a thing called the Iranian Genome Project, and Roxana is the de facto PI for this. She wrote the grant in my name. We got the money. She collected the samples, including trips to LA, but literally bringing together that community to get samples so that we can understand the genetic basis of the Iranian people, both how they're similar and how they're different, just as a side project. So it was the warfarin work, it was the Iranian work, it was the stuff in the lab. She's had a presence at the medical school that, as far as I understand, is legendary. And so the development of a scientist, along with the development of a person with these capabilities for bringing people together for scientific and other reasons, is just a potent combination. And I think you're going to hear what can happen when that combination exists in one person doing a PhD. So I think I'll stop and welcome Roxana to her defense.
Wow, that was intense. I feel like anything that happens after that could only be disappointment. Thank you everybody for coming. Today I would like to talk about personalized genomic medicine in understudied populations, and particularly I'd like to tell you two stories, one about clotting disorders and the other about the treatment of clotting disorders in African Americans. So, what is personalized genomic medicine? Since the draft of the human genome was first finished over a decade ago, we hear this term thrown around a lot. Time magazine would have you believe that it means that we could use genetic data to be able to predict the future of this baby. That might be a bit of a stretch. Some other individuals believe that it means that your DNA will tell you something about your susceptibilities and that maybe you'll make lifestyle changes based on what your genetic data tells you. So if you're at higher genetic risk for high cholesterol or diabetes, maybe you should lay off the burgers. The way that I like to think about personalized medicine is using genetic information in the context of the existing patient story to make decisions about disease risk and disease management. However, the challenge that exists in broadly implementing this is that genetic risk factors can be quite population specific. And I will share a few examples of this. For instance, there's a disease entity, hemoglobin disorders, where you have a weakening or destruction of the red blood cells. However, there are 3 distinct mutations that can cause this same phenotype, and they have very distinct global distributions. So if a researcher had only focused on this disease process in Asia, for instance, they would have completely missed the mutation from Africa that leads to the same phenotype. Additionally, the frequency of a particular mutation can vary across populations. Factor V Leiden is a mutation that causes increased clotting, and it's one that is often tested in the clinic whenever you have a family with a hereditary increase of clotting. However, as you can see, the mutation frequency is highest in the European population, and it's virtually absent in China and Zambia. Yet, if you have a patient with Chinese or African descent who comes into the clinic with this similar history, they usually still get tested for this mutation, even though that it's not particularly useful. The problem is that in disease genetics, most of our studies focus on European descent population. This trend has held over the past few years. About 70% of genetic studies looking at disease genetics are in European populations. 16% have a mixture of both Europeans and other populations. But usually the other populations that are included in the mix have fewer individuals. And 15% of studies focus only on non-European populations. Once again, these studies usually have much fewer people than the studies that have focused on European populations. This is a problem because the population that I'm particularly interested in, populations of African descent, have incredible diversity. What this graph shows is the probability that 2 populations share a variant based on the allele frequency of the variant. At a high level, if an allele is at lower frequency, it's more likely to be private to a single population. And that's a trend that you see across all of the pairwise comparisons. I'd actually like to draw your attention to the red and the dark purple, which is a pairwise comparison of African descent populations to Europeans and African descent populations to Asian populations. As you can see, this comparison has the least amount of sharing because Africans are incredibly diverse and incredibly different from other global populations. So ancestry is actually very important for genomic medicine because the higher genetic diversity in individuals of African ancestry means that there's probably a higher probability that the genetic mutations causing disease processes are population specific. Particularly, I'm going to talk about genetic factors of increased clotting and their treatment because the genetic factors affecting these 2 entities are not very well understood in African Americans. So the 2 stories, as I mentioned today, that I would like to talk about is how we figured out some genetic risk factors for clotting disorders, such as deep vein thrombosis and pulmonary embolism, and genetic factors that affect the therapeutic dose of warfarin, which is a blood thinner that is used to treat these disorders. In each case, I will be using a tool called exome sequencing. Exome sequencing sequences the exons and the flanking untranslated regions. An easier way to think about it is that it sequences primarily the regions responsible for coding for proteins. This comprises about 1 to 2% of the whole genome, and it's usually the part that it has the best functional story. So, with my first story, I'd like to talk about clotting disorders, such as deep vein thrombosis and pulmonary embolism. So, what are disorders of increased clotting? When you have too much clotting, this can lead to two disease entities called deep vein thrombosis and pulmonary embolism. In deep vein thrombosis, because you have increased clotting, you are prone to form clots, usually in the deep veins of the legs, which then impedes the blood flow, leading to inflammation, backup of fluid, and lots of pain. What can also happen is that this clot can become lodged from the vein, move through the venous system into the heart, and get pumped into the lungs. This is a medical emergency because now this clot is impeding blood flow to the lungs and you cannot get adequate oxygenation. Deep vein thrombosis and pulmonary embolism, according to the Center of Disease Control, is responsible for the deaths of 60 to 100,000 Americans each year. And it has a 30 to 60% higher incidence in African Americans. What are the factors that affect these disorders of increased clotting? Well, 100 years ago, a physician by the name of Rudolf Virchow first described the factors that can lead to clotting or increased clotting. They are endothelial damage, so if you have damage on the lining of your arteries, that tends to cause clotting because the clot is trying to fix the damage. Stasis, so if you go on a long plane ride or a long car ride, the blood begins to pool, and pooling blood is more likely to clot. And hypercoagulability, or hypercoagulable state. This is usually where genetic mutations come in. You have some genetic mutation for some reason that makes you more prone to clot because you can't break the clot down, or you're more likely to start the clot. To focus in on the hereditary component of this disease, we studied an African American family who had a distinct history of deep vein thrombosis and pulmonary embolism. In this pedigree, the blue indicates that the individual has had an event of either deep vein thrombosis or pulmonary embolism. And the red indicates that their disease process was so severe that they had to be put on long-term anticoagulation with the drug warfarin. So as we see here, we have an individual who has 3 daughters and a granddaughter who have all had this disease process. We had samples from 3 of these individuals that we then had exome sequences on. The first thing we did is look for clotting mutations that are often tested in the clinic. One of those, as I have mentioned before, is the factor V Leiden mutation, which has a 5% carrier prevalence in the European population and has a 5x increased risk of clotting. The other is a prothrombin mutation, which has a 0.7 to 4% carrier prevalence in the European population and leads to a 2 to 3x risk of clotting. Unsurprisingly, neither of these mutations were present. I say unsurprisingly because both variants are virtually non-existent in African descent populations. So, we decided to pinpoint what mutation might be responsible. The first thing I did is look at the number of heterozygous variants shared by the family because the disease process suggested a dominant mode of inheritance. There were over 13,000 variants that fit into this category. Next, we decided to focus on genes with biological relevance, genes that had been shown in the literature to have been implicated either through rare variants or